All right, so this is the second video for the tail end of the notes on equilibrium, and we're just going to look at Le Chatelier's principle here. Now, we're not going to go into a tremendous amount of depth with Le Chatelier's, but we are going to talk about it enough so that you understand the general concept. So basically, when you apply a stress to a system at equilibrium, the equilibrium is going to shift in some way that is going to reduce the effect of the stress. All right. So if you look at a general equation, some form of energy coupled with A and B is at equilibrium with C and D. And there are some factors that can affect equilibrium, right? If you change the concentration of any one of those items, then there has to be a change in order to adjust for that, right? If you change the pressure or the volume of a gas, that is going to change equilibrium, right? If you change the temperature, that's going to change the equilibrium. And if you add a catalyst, right? Now, let's explain why these things affect equilibrium in terms of what we learned in the last video, right? So for concentration, if you increase the concentration, then you're going to increase the number of collisions that should be occurring each second. Remember, more collisions, more likely that there is going to be an effective collision, and therefore you will end up with more reactions, all right? If you change the volume, let's say you decrease the volume, right? That would increase the pressure. So remember, volume and pressure are inversely related. So less volume equals greater pressure, right? Greater volume equals lower pressure. So if you decrease the volume, then we would increase the number of collisions, right? If you take the same amount of gas or same amount of reactants and you press it into a smaller container, now they're going to interact with each other more often. More interaction, right? More collisions equals a change in the rate of the reaction, right? A change in the equilibrium. Let's say you increase the temperature. Well, that's going to increase the number of collisions because now the molecules are moving faster, so they're going to bump into each other more often. It's also going to increase the energy of each collision, which more energy is obviously something there in that equation. More energy is going to affect equilibrium. And if you add a catalyst, right, um, catalysts are going to affect both sides, but pretty much the same, right? The equilibrium is not going to shift, but equilibrium is going to be reached faster, right? Because there is a lower activation energy. So the rate of the reaction will increase with the addition of a catalyst. So all of the things we learned about in the last video can be used to explain these four factors that are going to affect equilibrium. Le Chatelier's principle says this: if you change one of these four things, the system as a whole is going to respond in such a way to mitigate that stress, right? It's going to even it out. So let's look at some effects. We're going to look at this equation right here. Imagine we added Cl. Which way would equilibrium shift? So the addition of Cl2 is an increase to the concentration of reactants, right? So if I put more reactant in order to adjust for that, we're going to need to shift to the right because we need to make more products in order to balance out our equation. So we would probably say a shift to the right would fulfill Le Chatelier's principle if you added Cl2. What if we removed hydrochloric acid? So as the hydrochloric acid is being made, we're removing it. We're siphoning off the product. Well, I'm still going to get a shift to the right, right? The more product I remove, the faster A and B, right, H2 and Cl2 need to react to make up the difference to keep equilibrium the same. So we would shift again to the right. What if we increase the pressure? Well, in this case, I have all gases. So increasing the pressure would actually lead to no change at all, okay? Because all the gases would be experiencing the same increase in pressure. What if we decrease the temperature? Well, this would actually probably shift us to the right, okay? Because with lower collisions, it's less likely for my HCl to break apart, okay? With lower speed there. Let's say we removed some H2. Well, now we're going to shift to the left, right? We don't have enough of a concentration of reactant in order to keep making product, so we're going to shift back to the left. Let's say we increase the temperature. Well, actually, in this case, we would shift to the left, all right? The H2 and Cl2 would possibly be formed at a faster rate because the HCl might decompose, right? So there's a lot of different things we can change. We just want to be able to explain, is the reaction going to shift to the more production on the right side of the arrows or more to the left? Let's look at another one. Let's look at this reaction right here. Iron 3 nitrate and potassium thiocyanate, that's KSCN, is at equilibrium with this iron thiocyanate species, this iron thiocyanate nitrate species, and this KNO3, which would be potassium nitrate. All right. Now, this is the molecular equation for what we have going on here. The net ionic equation, which is something we'll talk about if you take AP, is just this. The iron on the iron nitrate species is reacting with the thiocyanate on the potassium thiocyanate species, and we're getting this iron thiocyanate as a reaction or as a product. Now, the reason we leave them out, they're called spectator ions. Their charge doesn't change, their state doesn't change. They're just swapping partners. But the iron is actually changing and the thiocyanate is changing. So iron 3 plus, this compound or this ion, is a yellow substance. Thiocyanate is colorless, and iron thiocyanate is a blood red color. So if we're doing this reaction and we can manage to change these four factors, then any shift in the equilibrium will result in a color change. If we get a lighter shift, right, from red to yellow, then we know we're shifting to the left. If we have a darker color change, right, we get more to the red, then we're getting a shift to the right, okay? So let's look at this equation. And again, we have, this is yellow. Oh, let's do this in a different color. All right, so remember, iron is going to give us a yellow color to our solution, and this iron thiocyanate is going to be red, and we can ignore the SCM because it's colorless. All right, so I'm going to give you a stress. We're going to try to predict the color change. Okay, so let's say we increase the amount of FeCl3, the amount of iron chloride. I guess that would be iron ferrochloride. It'd be ferrochloride. What's going to happen? Well, if I put more reactant in, the concentration of the reactant goes up, so we would expect it to shift to the right, right? We'd make more product. Well, in that case, we're going to get a darker color, okay? Because the equilibrium needs to shift to get rid of these Fe3 plus ions that we're adding. All right, so we would think the color change would be more to the red, and we're going to the right. And our explanation is we need to get rid of the additional iron 3, right? We need to react it away to make more product. What if we added KNO3? All right, well, both K and NO3 are spectator ions, right? We don't see them in our net ionic equation there. So we would have no color change and we would have no shift. And the reason is they are spectators, right? Spectator ions. They're not participating in this specific color change reaction. Let's say we added more ammonium thiocyanate. All right, well, that's a thiocyanate, or yeah, on a thiocyanate on the reactant side. So again, we would expect to get a red color change because we're going to shift to the right. Because since I'm putting in more of my reactant, I expect to make more product. All right, what if we heated it? All right, well, in this instance, we would need to know a little bit of information about whether this is endothermic or exothermic. In this case, we would actually expect to get a yellow color, which indicates a shift to the left. And the reason for that is that the equilibrium is going to favor the endothermic reaction, which is actually the reverse reaction. So we would favor the reverse endothermic reaction. Well, how would I know that? Well, I would need a graph that looks something like this. And it would have to look like this in this case. Fe and SCN. Right? And then there's my FeSCN plus 2. So in this case, because I'm favoring an endothermic reaction when I heat something, I would have to be going that way. And so since I'm going that way, I know I'm getting towards the yellow side, so I would expect a lighter reaction. What if we cooled it down? Well, if we cooled it down right, we would expect it to be the opposite. We would say, okay, it's going to end up being red. And because when we cool something down, we're actually going to favor the exothermic reaction. And so in this case, because I know what the graph looks like, I would expect it to go to the right, and over here on the right is the red color. Let's say I added some silver nitrate. All right, well, this would actually give us something completely kind of different. This is just kind of like a trick question, or not a trick question, but this would be like a challenge question. What would happen if we added a silver nitrate in there? Well, we know silver nitrate is soluble because all nitrates are soluble. So we would expect the SCN to be replaced by that nitrate, and so we would shift over to the yellow side. All right, now this would be a challenge one, so don't worry. We're actually just going to leave that out. If we were in person school, we would actually draw that one out. We would do this reaction. We would look at it. Don't kind of worry about that one. Just worry about the first 5. Now that I'm sitting here looking at it, that one's a little harder to explain if we don't have the reaction in front of us. So just make sure you understand the first 5. All right. So when we talk about these things, okay, a lot of it has to do with talking out the reaction. Like if I put some of this in here, what do I expect it to make? I don't expect you to get these on the very first watch, right? You might need to go back and watch this more than once. You might need to read the textbook selection that I have for this week more than once. If you get stumped, I know this stuff can be challenging. Please email me or send me a message, right? Let me help you. If you need help, I'm more than willing to help. Just send me an email or reach out, all right? I'll see you guys in the next video.